Good morning everyone. In this lecture, we'll see about the square column footing. Myself, Dr. J. Sayaruban, Professor and Head, Department of Civil Engineering, Rohini College of Engineering and Technology. Let us see the problem. Design an isolated footing of uniform thickness for RCC bearing, a vertical load of 600 kN and having a size of 500 by 500. As a column size is given by 500 by 500. The shape bearing capacity of the soil is taken as 120 kN per meter square. Use M20 and Fe415 steel. So size of the column given by 500 by 500. Then a load is given by 600 kN. Shape bearing capacity is 120 kN per meter square. Then characteristic tensile strength 415 Newton per mm square. And FCK is equal to 20 Newton per mm square. So next we will find out the size of the footing. So we know the given value is 600 kN, that is the load on the member is 600 kN. So let us assume the self height of the footing, normally we have to increase by 10%. So we have to just increase this load 600 by 10%, we will get a value of 660 kN. So total load is 600 plus 60, 10% increasing in load. That is 60, that will be is equal to 660 kN. Next we have to find out the area of the footing by load by SBC, that is a bearing capacity. Load already we find out the value of 660 divided by 120, we will get a value of 5.5 meters square. So let us assume this is a square column. So A square is equal to 5.5 meters square. So the area you have to take it as square root of 5.5. So we will get a 2.35. So size of the column or size of the footing we have to provide by 2.35 by 2.35 meter. That is that size we have to find out using this load. Just increase the load by 10%. From that loading condition we have to find out the size of the footing. So finally we have to fix the sizes 2.35 into 2.35 meter. Next we have to find out the net upward pressure. So net upward pressure nothing, P0 is equal to load by within the area of the footing. So that load is 600 divided by 5.5. We will get a value of 109.01 kN per meter. Next, the depth on basis of bending compression. We have to find out the depth here. So M is equal to, that bending is equal to P0 by 8, B minus B into B minus B by 4. So we know the value, substitute all the values here. There is B0 is a net upward pressure, that is 109.01 divided by 8. 2.35 minus B is a column size 0.5. Then overall width of the footing is 2.35 minus 0.5 divided by 4. So that will be is equal to 56.08 kN meter. Then factor moment 1.5 into 56.0608. So we will get a value of 84.12 kN meter. That is mu, factor moment mu is equal to 84.12 kN. Then ultimate moment we have to find out by using this relation, that is 0.36 xu max by d into FCK into 1 minus 0.40 xu max by d into BD square. So substitute the values here and finally we will get a value ME limit is equal to 2.76 BD square. From equate moment is equal to limiting moment. So 2.76 into B into D square. So we will get 84.13 into 10 power 6. Finally we have to find out the D value, what that is 130.91. That will be is equal to 115 mm. So overall depth of the footing is equal to D plus cover. So D for a footing we have to provide a 60 mm cover. So the overall depth D is equal to 175 mm. Next we have to find out depth basis on two-way shear. So let us assume that percentage of steel reinforcement is 0.3%. From we have to find out the value of tau c. For 0.25 is 0.36, for 0.5 is 0.48. From we have to find out the value for table number 19 of 5 is 456 2000, that is equal to 0.38. Then permissible shear stress we have to find out by taking the modification factor. So tau is equal to 1.25 into 0.38. finally we'll get a value of 0.475. So tau v is equal to 0.475. Normally in the foundation, the critical section lies d distance from the face of the column. So A is equal to B by 2 minus B by 2. So substitute the value here. Finally A is equal to 425 mm square. So VU is equal to, that is shear stress is equal to 1.5 into P naught into A. Substitute the value here. Finally we will get a value of V is equal to 151.36 Newton per mm square. So here P naught is the net upward pressure. This is the total area. So tau v is equal to V by BD. So finally substitute the values here. We will get a value of D. So D is equal to 318.7 mm. That will be equal to 320 mm. So based actually that we have to determine the D. The critical section lies normally D distance from the face of the column. So from that we have to use this relation. Finally we find the value of D is equal to 320 mm. Next, depth based on two-way shear. So B naught is equal to D by 2 plus D by 2 plus B. So D is equal to 320 mm, B naught is equal to 820 mm. Shear force is equal to F is equal to B naught into B square minus B naught square. Substitute the value here, 110 into 2.35 square minus 0.82 square. So F is equal to 532.61, that's approximately that will be equal to 530 kilonewton. So ultimate load shear is equal to Fu is equal to 1.5 into 530. So that will be equal to 595 kilonewton. Next we have to find out the shear stress. So the shear stress tau v is equal to Fe by 4 into B into D. So tau Fe already find out 795 into 10 power 3 divided by 4 into 820 by 320. That will be equal to 0.757 Newton per mm square. Then we have to find out the permissible shear stress. That is tau v is less than or equal to Ks into tau c. Ks is equal to 0.5 into beta c. That is beta c is equal to shorter side of the column divided by longer side of the column. So that will be equal to 500 divided by 500 equal to 1. So Ks is equal to 0.5 plus 1. So that will be equal to 1.5. So take Ks value as 1. Tau c is equal to 0.25 into square root of fck. So substitute the value here, we will get a tau c value 1.118 Newton per mm square. So Ks into tau c, that is Ks already we find out by 1.5. 1.5 we have to take it as 1. So 1 into 1.118. So that will be equal to 1.118 Newton per mm square. So tau v is less than tau c. Hence the design is safe. Next, design of reinforcement. So we have to find out the reinforcement by using this relation. M is equal to 0.87 Fy AST into D, 1 minus Fy AST divided by BD into FCK. So substitute the values, all the values, and finally we will solve by AST is equal to 745 mm square. So provide 7 numbers of 12 mm diameter bar at 150 mm center to center. So area of steel is equal to 745 mm square. From that we have to use 12 mm diameter bar. Then 7 number we have to use it, but the spacing of 150 mm center to center. Next, check for development length. So L is equal to 47 pi. 47 into pi 12 mm, so 564 mm. So the L0 is equal to 1 by 2 into B minus DC. So substitute all the values here. L0 will get 65 mm. So here that L0 is greater than LD. So this is safe against the development length. The transfer of load at the column base. So using this relation, 2 by 1 is equal to B naught by 385. That will be equal to 770 mm. So A1 is equal to 500 plus 770 into 770 square. That will be equal to 2040 square. A2 is 500 square. So adapt minimum values to square root of A1 by A2 is equal to 2 from page number 65 of IS 456 2000. Then that will be equal to 4.08. So adapt value of square root of A1 by A2 is equal to 2. Permissible bearing pressure, that is 0.45 fck into root of A1 by A2. So 0.45 into 20 into 2, that will be equal to 18 Newton per mm square. Next we have to find out the actual bearing pressure. So that will be equal to load by area, that is 600 divided by 500 into 500. So we will get a value of 2.8 Newton per mm square. So then finally you have to check the actual bearing pressure with the permissible bearing pressure. Here that actual permissible bearing pressure is 2.8, that permissible is 18, hence the design is safe to carry the load. Thank you.